Memory organization. Presented by Adarsh Krishna. Memory hierarchy. The memory unit that communicates directly with the CPU is called the main memory. Devices that provide backup storage are called auxiliary memory, magnetic disks and tapes. Cache is a very high-speed memory used to increase the speed of processing by making current programs and data available to the CPU at a rapid rate. Cache compensates the speed differential between main memory access time and processor logic. Main memory. Most of the main memory in a general-purpose computer is made up of RAM integrated circuit chips, but a portion of the memory may be constructed with ROM chips. Integrated circuit RAM. Random access memory. Chips are available in two possible operating modes, static and dynamic. Filled circle static RAM consists of internal flip-flops that store the binary information. The stored information remains valid as long as power is applied to the unit. Easier to use and has shorter read and write cycles. Filled circle dynamic RAM stores binary information in the form of electric charges that are applied to capacitors. The stored charge on the capacitors discharge with time, and the capacitors must be periodically recharged by refreshing the dynamic memory. Reduced power consumption and larger storage capacity in a single memory chip. ROM, read-only memory, is used for storing programs that are permanently resident in the computer that do not change in value once the production of the computer is completed. ROM portion of main memory is needed for storing an initial program called a bootstrap loader. RAM chip. Filled circle bidirectional data bus that allows the transfer of data either from memory to CPU, read operation, or from CPU to memory, write operation. Filled circle. The capacity of the memory is 128 words of 8 bits per word. This requires a 7-bit address and an 8-bit bidirectional data bus. Filled circle. The read and write inputs specify the memory operation. Filled circle. The two chip select CS control inputs are for enabling the chip only when it is selected by the processor. Filled circle. The function table specifies the operation of the RAM chip. ROM chip. ROM can only read. The data bus can only be in an output mode. For the same size chip, it is possible to have more bits of ROM than of RAM, because the internal binary cells in ROM occupy less space than in RAM. For this reason, the diagram specifies a 512-byte ROM, while the RAM has only 128 bytes. The 9 address lines in the ROM chip specify any one of the 512 bytes stored in it. ROM. Filled circle. ROMs permanently stores bit values. Filled circle. At the time of manufacture, a diode is present at the intersection of a data line and an address line. Filled circle. In a memory cell, if a diode is present, the diode starts conducting and therefore the corresponding data line become high. Filled circle. If a diode is not present, the corresponding data line become low. Filled circle. Thus, whether a 0 or 1 is stored in a memory cell is determined by the presence or absence of a diode. Filled circle. The data that are stored in a ROM chip is programmed at production and no later changes are possible. PROM. Filled circle. Structurally similar to ROM. Filled circle. At every intersection there is a fuse. Filled circle. A charge sent through a column will pass through the fuse in a memory cell to the bit line indicating a value of 1. Filled circle. Initial state of PROM chip is all ones. Filled circle. A PROM writing device is used to inject current flow through the required fuses. Filled circle. Unlike ROMs, PROMs can be programmed once. EEPROM. Filled circle. At every intersection there is a transistor, floating gate metal oxide semiconductor, FGMOS. Filled circle. When a high voltage is applied to a transistor, the electrons accumulate on the floating gate, avalanche injection. Filled circle. These trapped electrons continue to be present even when the high voltage is removed. Filled circle. Data stored in EEPROM can therefore be retained even for decades. Flash memory. Filled circle. Memory cells are made from floating gate MOSFETs. Filled circle, it can either write or erase and write multi-kilobyte of data in a single operation. Filled circle access time is several hundred times faster than EEPROM. Filled circle 2 types NOR flash, NAND flash. SRAM. Filled circle, these are memories that consist of circuits capable of retaining their state as long as power is on. Filled circle uses 6 transistors to form a special flip-flop circuit that can store a logic 1 or 0. Filled circle expensive. Filled circle faster than DRAM. DRAM filled circle, the main memory is generally made up of DRAM chips. Filled circle information is stored in a DRAM cell in the form of a charge on a capacitor. Filled circle, this charge needs to be periodically recharged. SDRAM. These RAM chips' access speed is directly synchronized with the CPU's clock. For this, the memory chips remain ready for operation when the CPU expects them to be ready. Data transfer takes place both in the falling and rising edges of the clock, faster operation. DDR-SDRAM is a faster version of SDRAM. RDRAM. Rambus DRAM. It provides a very high data transfer rate over a narrow CPU memory bus. It uses various speedup mechanisms, like synchronous memory interface, caching inside the DRAM chips, and very fast signal timing. The Rambus data bus width is 8 or 9 bits. Associative memory. The time required to find an item stored in memory can be reduced considerably if stored data can be identified for access by the content of the data itself rather than by an address. A memory unit accessed by content is called an associative memory or content addressable memory, CAM. This type of memory is accessed simultaneously and in parallel on the basis of data content rather than by specific address or location. When a word is written in an associative memory, no address is given. The memory is capable of finding an empty unused location to store the word. When a word is to be read from an associative memory, the content of the word, or part of the word, is specified. The memory locates all words which match the specified content and marks them for reading. An associative memory is more expensive than a random access memory because each cell must have storage capability as well as logic circuits for matching its content with an extern. Hardware organization. It consists of a memory array and logic for M words with N bits per word. The argument register A and key register K each have N bits, one for each bit of a word. The match register M has M bits, one for each memory word. Each word in memory is compared in parallel with the content of the argument register. The words that match the bits of the argument register set a corresponding bit in the match register. After the matching process, those bits in the match register that have been set indicate the fact that their corresponding words have been matched. Reading is accomplished by a sequential access to memory for those words whose corresponding bits in the match register have been set. The key register provides a mask for choosing a particular field or key in the argument word. The entire argument is compared with each memory word if the key register contains all ones. Otherwise, only those bits in the argument that have ones in their cores. Associative memory of M word, N cells per word. The relation between the memory array and external registers in an associative memory is shown in figure. The cells in the array are marked by the letter C with 2 subscripts. The first subscript gives the word number and the second specifies the bit position in the word. Thus cell SIG is the cell for bit J in word I. A bit AJ in the argument register is compared with all the bits in column J of the array provided that KJ equals 1. This is done for all columns J equals 1, 2, N. If a match occurs between all the unmasked bits of the argument and the bits in word I, the corresponding bit MI in the match register is set to 1. If one or more unmasked bits of the argument and the word do not match, MI is cleared to 0. Cache memory. Locality of reference. Cache memory is based on the principle of locality of reference. Locality of reference. Locality of reference refers to a phenomenon in which a computer program tends to access same set of memory locations for a particular time period. Temporal locality. Temporal locality means current data or instruction that is being fetched may be needed soon. Spatial locality. Spatial locality means instruction or data near to the current memory location that is being fetched, may be needed soon in the near future. If the active portions of the program and data are placed in a fast small memory, the total execution time of the program can be reduced. A fast small memory placed between the CPU and main memory is referred to as a cache memory. The cache memory access time is less than the access time of main memory by a factor of 5 to 10. The cache is the fastest component in the memory hierarchy and approaches the speed of CPU components. The fundamental idea of cache organization is that by keeping the most frequently accessed instructions and data in the fast cache memory, the average memory access time will approach the access time of the cache. Although the cache is only a small fraction of the size of main memory, a large fraction of memory requests will be found in the fast cache memory because of the locality of reference property of programs. Operation and performance. When the CPU needs to access memory, the cache is examined. If the word is found in the cache, it is read from the fast memory. If the word addressed by the CPU is not found in the cache, the main memory is accessed to read the word. A block of words containing the one just accessed is then transferred from main memory to cache memory. The block size may vary from one word, the one just accessed, to about 16 words adjacent to the one just accessed. In this manner, some data are transferred to cache so that future references to memory find the required words in the fast cache memory. Hit ratio. The performance of cache memory is frequently measured in terms of a quantity called hit ratio. When the CPU refers to memory and finds the word in cache, it is said to produce a hit. If the word is not found in cache, it is in main memory and it counts as a miss. The ratio of the number of hits divided by the total CPU references to memory. Thank you.